Hello and welcome. I'm Ensiyeh Keshtkaran and I'm delighted to present this research on behalf of the team. In this study, we estimate the blood alcohol concentration through the facial features for driver impairment assessment. Please stay with me. Despite progress made by safety advocates and law enforcement, drunk driving still remains the #1 cause of traffic death globally, claiming roughly 10,000 lives and costing approximately $194 billion each year in the US. In 2021, the US government introduced mandate for the Department of Transport to assess technologies for drunk driving detection system in vehicles. This is currently an open call technology, which means there is a need for scalable and cost-effective technologies to efficiently detect alcohol intoxication impairment in drivers. The current approaches for detecting drunk driving mostly centers around analyzing driving behavior indicators, such as driving and steering pattern and pedal usage. The problem is that this needs the potential impaired driver to be driving on the road, endangering themselves and others until their behavior can be recognized as a sign of being drunk. Some other approaches incorporate external sensors like alcohol detection or touch-based sensors, but sensors usually require regular maintenance, and the approach is limited to the vehicles equipped with the sensor technology. There are very few studies looking at using computer vision for identifying drunk driving. However, they tend to heavily rely on advanced camera-based sensors, such as eye tracking systems and in-vehicle monitoring setup, rendering them less practical for widespread adaptation. The other limitation is that there isn't any suitable database for this field yet. Current databases are either from people pretending to be drunk, or they are collected using advanced eye tracking system and advanced vehicle-based sensors, or they are not extensive enough to reflect the real-life situations and individual variations in the alcohol effects. Now, considering these limitations, our contributions become evident in two distinct ways. We present a machine learning system that utilizes cues from standard RGB videos of driver's face to detect the degree of alcohol-related impairments. To train and test our system, we created a dataset with simulated driving videos featuring 60 participants at 3 distinct intoxication levels: sober with a BAC level of 0, low intoxicated with a BAC level between 0.05 and 0.07, and severely intoxicated with a BAC above 0.08. Let's look at our system's workflow. The first part is the data collection, of course. We collected data from actual alcohol-impaired drivers within a controlled but realistic environment. The selection of type of alcohol in our study was intentionally diverse. We allowed participants to choose what they usually drink in their usual life to replicate their real-life scenarios as close as possible. The process was as follows. At each level of alcohol intoxication, participants engaged in 10 minutes driving using the driving simulator. The initial target BAC was set at 0, which is considered as a sober state. After driving for 10 minutes at sober state, participants began consuming alcohol and tested their BAC using a breathalyzer until they reached to the second level of intoxication. The second BAC target was set to BAC between 0.05 and 0.07 and referred to as low alcohol intoxication impairment. After driving for 10 minutes at this low level of intoxication, participants consumed additional drinks and tested their BAC levels until they reached to the final target BAC level. And the final BAC target level was above 0.08 and referred to as severe alcohol intoxication impairment, and participants completed another 10 minutes of driving on a simulator when they were at the final stage of intoxication. We developed our research simulator by integrating a research-grade simulator software with a commercially available driving monitoring system. The simulator has two-stage ignition and engine start process that replicates the actual vehicle activation. It also has a driver ID tag reader. We have also integrated an alcohol breathalyzer module to it. The simulator includes RGB video recordings of the driver's face along with 3D and infrared video of the driver's face. However, for our baseline study, we have chosen to only utilize the face RGB videos. It also records rear view RGB videos showing driver posture and steering interactions. Driving simulation event logs and screen recordings of driving behavior are also included. Once we had the data collected, for the video feature extraction, we started by identifying features that have the capacity to reflect the pathophysiological alternations resulting from alcohol intoxications, as documented in existing literature. Existing research says that the alcohol intoxication mainly affect changes in the eye features, gaze pattern, and facial expression. So based on this, we extracted eye landmarks, gaze direction, PDM parameters, which quantifies the extent of facial landmark shape variations, as well as the facial action units and head pose. These features values were extracted for each frame from RGB videos by using the OpenFace software library. Then we calculated the average feature values over window size of 150 frames. We used t-test analysis to compare the changes in calculated average across different levels of intoxication. Finally, the features that showed the most significant variation across various levels of intoxication were visualized. The final feature selection was based on, first, their strong alignment with the documented pathophysiological changes associated with alcohol intoxication, and second, their ability to show significant variation across different levels of intoxication. So the eye aspect ratio, head and gaze movement, and PDM scale showed noticeable changes in behavior across varying levels of intoxication, and hence they became our selected features for this baseline study. As the degree of alcohol intoxication increases, a corresponding reduction in the EAR can be observed. This is accompanied by heightened change in the head position and the gaze angle, as well as a raise in P scale variation at the lower level of intoxication. These findings is consistent with what is in literature. So based on the studies, the primary indications of alcohol-induced intoxication is heightened emotional expression, reflected in our increased head movement and P scale features, and a tendency for their eye to appear less open, showing a fatigue as a result of being intoxicated, which is linked to our reduced EAR feature. For machine learning, we built and tuned LSTM neural network. LSTM was selected because of its capability to process sequential data, considering the temporal independencies in our feature. For the tuner, we employed Bayesian optimization. Then we train our LSTM model using the best hyperparameter defined by the tuner. The loss function we use is a sparse categorical cross entropy loss because we aim to do 3-class classifications where each sample belongs to exactly one class out of the 3 classes of sober, low intoxicated, and severe intoxicated. Our model can classify alcohol intoxication levels with the accuracy of 75% solely based on signs of intoxication that can be captured through conventional RGB cameras. Our system has notable strength in the sober classes, and balanced F1 score and consistent macro and weighted average suggest a generally stable and balanced performance across the 3-class classifications. Looking at our model's efficiency through the confusion matrix, our model has significant true positive rate of about 85% for correctly identifying instances of sober driving state, 71% and 72% for the low alcohol intoxication and severe alcohol intoxication states, respectively. We also examine how robust our model results are when exposed to different subsets of data during the training and evaluation phases. As you can see on the top table, the uniformity of the result produced by the model across different instances of data sets confirms that the model generalized quite well. Last but not least, for us to understand the significance of each features on predictive performance of our model, we conducted a feature importance analysis through which we took off one feature at a time and we retrain and reevaluate our model on the remaining 3 features. The results as shown in table 4 indicates that in order of significance, PA scale, gaze angle, EAR having the most significant effects on the model accuracy. Thank you for your time. For more details about cited works in this presentation, please refer to references section in our paper.